Result from Python program for random forest k-fold diagram connecting all nodes using Plotly with dark background. Pradeep K. Suri, author, researcher, consultant, and AI/ML architect. Power of the video. Architecture. 1. Represents the full ML lifecycle pipeline. Inputs, simulate raw features or signals from multiple data sources, structured, unstructured. Folds, represent different partitions of training data allowing cross-validation for generalization. Trees, simulate multiple models or decision trees emphasizing the ensemble concept. Outputs, final predictions or classifications from combined models. Brain architectural strengths. 1. Ensemble learning visualized. Random forest uses multiple decision trees to make robust predictions. Each tree is trained on different fold samples, reducing overfitting. Voting or averaging from all trees leads to improved accuracy. 2. Cross-validation built in. The use of 10-fold CV improves model robustness. Helps to prevent overfitting and estimates performance better on unseen data. 3. Modular, scalable design. You can scale the number of inputs, folds, trees, or outputs to simulate complex models. Supports parallelism, especially useful in distributed systems or big data environments. 4. Excellent educational and explainable AI tool. Helps students, researchers, or stakeholders understand how ensemble models and k-fold training work. Can be adapted to explain bias variance trade-off, feature importance, or voting mechanisms. Factory domains where this architecture can be applied. Brief Case 1. Finance. Credit scoring, fraud detection, and loan risk modeling. Multiple features, credit history, transactions, etc., rightward arrow folds, rightward arrow ensemble classifiers, rightward arrow risk prediction. Hospital 2. Healthcare. Diagnosis prediction, drug recommendation, patient risk stratification. Inputs equals health parameters, folds equals stratified CV, outputs equals disease risk/treatment outcome. Factory 3. Manufacturing/Industry 4.0. Predictive maintenance, quality control, supply chain optimization. Sensor readings, images, or logs, rightward arrow folds, rightward arrow multiple AI models, rightward arrow maintenance alerts or defect prediction. Mobile phone 4. Telecom and IT. Churn prediction, network fault detection. User activity logs, rightward arrow folds, rightward arrow decision models, rightward arrow alert on churn/failure. Test tube 5. Scientific research/bioinformatics. DNA sequences, chemical structure, clinical trials. Inputs equals features from sequences, folds equals sample sets, trees equals classifiers, rightward arrow biomarker discovery. Chart increasing 6. Marketing and sales. Customer segmentation, recommendation engines. Behavior data, rightward arrow folds, rightward arrow ensemble recommenders, rightward arrow product suggestions. Robot Phase 7. AI engine development. Train and validate multiple ML algorithms in ensemble fashion. Useful for auto ML pipelines, feature selection, or stacking architectures. Glowing star bonus, extendable ideas. Counterclockwise arrows button, add attention weights to input/fold/trees to simulate weighted ensembles. Package replace trees with other models, SVMs, neural nets, to visualize heterogeneous ensembles. Receipt add label/metrics to visualize accuracy, precision, recall per tree or fold. The Python program leverages random forest combined with k-fold cross-validation to simulate predictive modeling in the aerospace industry. Let's explore the power and impact of this program from the management and aeronautical engineering perspectives. 1. Power for management. For aerospace managers or industry leaders, this program provides a robust and data-driven decision-making tool. Here's how it benefits management. A. Strategic decision-making. Improved decision support. Management can make informed decisions based on predictive models that anticipate failures, estimate remaining useful life, RUL, of components, or forecast maintenance schedules. Cost optimization. By predicting failures and maintenance needs accurately, the aerospace company can reduce unnecessary part replacements and optimize maintenance schedules, ultimately saving on unplanned downtime and maintenance costs. Risk management. The outputs like failure type or severity score give managers insights into critical system failures before they occur, allowing them to better manage risks associated with component failure and operational disruptions. B. Operational efficiency. Predictive maintenance. The program helps forecast when and where maintenance needs to occur, which leads to higher fleet availability, fewer delays, and increased productivity. Resource allocation. Managers can allocate resources more effectively by using these predictions to plan labor and part inventories in advance, ensuring they are prepared for potential failures. C. Cost and time management. Optimizing repair schedules. By predicting component failure or wear, it allows managers to schedule repairs during planned downtime rather than emergency repairs, avoiding expensive emergency maintenance or even catastrophic failure. Life cycle costing. Predicting remaining useful life, RUL, enables managers to assess and plan the full life cycle costs of components, providing better forecasting for capital expenditures. 2. Power for aeronautical engineers. For aeronautical engineers and maintenance engineers, the program serves as an advanced tool to predict, optimize, and enhance the engineering processes that go into maintaining aerospace systems. Here's how the program would empower engineers. A. Failure prediction and analysis. Predictive analytics. Using data from various system parameters, sensor data, flight conditions, component age, maintenance history, the program predicts when and which components are likely to fail. This empowers engineers to make data-driven decisions for repairs and replacements before critical failures occur. Severity scoring. The program calculates the severity of possible failures, so engineers know not just when to fix a part but how urgently the issue must be addressed. This is critical for aircraft safety, where even minor component degradation can lead to larger issues. B. Maintenance scheduling. Optimal repair timing. With predictions about when components will fail and what their remaining useful life, RUL, is, engineers can schedule repairs during low-demand periods or scheduled maintenance windows, ensuring minimal impact on flight operations. Component lifespan optimization. By analyzing data from various sensors, engineers can determine the most optimal time for component replacement or repairs, preventing unnecessary replacements or delays in the repair cycle. C. Quality and performance improvement. Root cause analysis. Engineers can use the predictions to investigate patterns of failure, determining the root cause of issues that may not be apparent from standard inspection processes. Enhanced quality control. The program allows engineers to identify weak spots in the design or manufacturing process. This enables continuous improvement in the quality and performance of aerospace systems, directly contributing to safer, more reliable aircraft. 3. Broader impact and industries. The architecture of this program has broader implications in aerospace engineering, especially when it comes to handling large-scale data in predictive maintenance and optimization. Here's how. A. Data integration. The ability to integrate sensor data, maintenance records, environmental factors, and operational conditions into a predictive model like this helps engineers, operations teams, and managers to leverage big data for operational decision-making. This holistic approach improves not only operational efficiency but also safety standards. B. Simulation and testing. Simulated cross-validation. With tenfold cross-validation, the program provides a robust framework to test various data-driven hypotheses. Aeronautical engineers can simulate different failure scenarios and analyze predictions across multiple testing sets to enhance their understanding of system behavior. C. Safety assurance. Critical systems monitoring. Aerospace engineers are responsible for ensuring safety-critical systems function as expected. Predicting component failures and analyzing system health can significantly enhance safety and prevent catastrophic failures in flight. 4. Impact on the aerospace supply chain. Supply chain optimization. The ability to predict failures in components means that parts can be ordered just in time before they're actually needed, reducing the need to stock expensive spare parts and improving inventory management. Collaboration between manufacturers and operators. Manufacturers can collaborate with operators to ensure that the parts they produce align with the predictions made by this model. For example, predicting maintenance schedules might align with parts production cycles, improving overall supply chain efficiency. 5 real-world examples of impact. Aircraft engine monitoring, predicting when an engine component is likely to fail, such as a turbine blade, can allow for scheduled maintenance before failure occurs, avoiding significant engine downtime and repair costs. Component health monitoring, using sensor data, temperature, vibration, pressure, this model could predict potential failures in components like landing gear, hydraulic systems, or flight control systems. Conclusion. The power of this program lies in its ability to 1. Predict component failure and assess remaining useful life, RUL. 2. Enable data-driven decision-making for optimal maintenance and repair scheduling. 3. Improve safety, efficiency, and cost-effectiveness across the aerospace industry. For both aerospace managers and aeronautical engineers, this program offers a tool for proactive decision-making, ensuring higher safety standards, better resource management, and more efficient operations in the aerospace domain. It also fosters a culture of continuous improvement where data drives smarter decisions in an industry where precision and safety are paramount. Thank you.